Um, see. Yep. Okay. We're good. Hello everyone, and welcome to today's live stream, where we will be exploring some of the ideas that I've been thinking about, and a few other things that we've been developing at Dialect Technologies. Um, in today's live stream, we will mostly introduce this project and also talk about why this project exists, what we'll be doing, and why it's important, mostly. And the reason, let me see. Okay, okay. Trying to do this again. I'm sorry about that. I need to fix my mic first. I think I'm good. Good. Yes. All right. So as I was saying, this project is uh, mostly what we want to do from this point on is introduce the project, which I think um, we will be from now on. We'll be doing live science, live coding throughout the time, and also talk about other things that are mainly important for this project. So I will just walk you through what we'll be doing in the next couple of weeks and um, the plan and the strategy, and also show later on what we have already, and a few other demos to display the results we have. So the live stream, so the heading is a bit like for this heading is it's a bit too specific, but generally the project is to try and experiment with adaptive predictive models. And uh, so the heading we have right now is non-stationary predictive coding lab. I think probably we don't need lab, but anyways. So non-stationary is just if you think about chaotic environments, chaotic systems like the weather or even the brain itself, it's I wouldn't say the brain is chaotic, but sometimes it might be chaotic. But non-station every stationary just means it changes with time. So time is an important factor for this case because with time the state of the system changes. So what are we going to do in this project? So the live stream is also, is just to do a live research and live science, and then talk about a series of things we'll be doing, like building an online predictive coding controller. And the coding controller is supposed to be trained or to do to help us understand how systems like these can survive in a world where rules change all the time. So by rules, I mean all the systems we know of play or operate under some sort of rules, right? And those rules usually are not static. They change all the time. The rules of the weather also change all the time. The rules of um, a thinking system changes all the time. So our goal is to try and study these systems that can do or predict very well, or try to predict how these rules changes, or how systems like these change over time. Now, the system I'm calling the predictive coding mod controller is just it controls or it controls a system. So if a system lives in an environment and this environment changes all the time, it must have a model in itself that enables this system to, operate in that environment. So um, what that thing is, what that thing that controls that system is what we want to try and experiment with, and see where we can go. So the big picture is the predictive model, the predictive system, coding system that lives in such a stationary system. Stationary is a world that changes. Partially observed world rule. So the rules here we also it can apply to the physical rules or um, the mental rules for that specific system in that specific environment. And the environment is a dynamical system. So dynamical is the same as changing all the time. So it's dynamics. It changes as time goes by. And then the goal is to design and a controller and a predictor that can also can help us understand these systems and the environment they operate in. So in a measurable way. So we have to measure and see the data and also interpret the data well. And so the research here will be guided by these documents. So we'll be going through every week step by step through the research, and the research will be live. We'll do some experiments on live and then also do some coding as well. And so what regime robustness means? So regime is just environment, and robustness is how robust that environment can be. And by regime robustness, we mean like we want to so we care about more than just raw predictive accuracy. So by that I mean like we want to understand the system itself plus the environment itself. So if the system can predict very well, or we can predict how what the system does very well in a specific environment, we also have to know that we also have to decide or to change the environment as well and see how well the system can operate on a different environment. So the environment can be multidimensional. Robustness can also, if it's a multi-dimensional environment, then we we automatically we know that robustness can also be multi-dimensional. So key robustness dimensions are low detection delay when the world changes, and so every time the world changes, like it's hard to detect when a world changes, especially if um, it's not so obvious that something has changed in the world. It's hard to detect something like that. And then so it has to be like a low. It has to operate on a very low delay. So the system has to be alert all the time so that it detects the changes in the world. And then fast recovery after change. So low regret. So fast recovery after change. So if the system, the world changes all the time, then the system also has to um, change with it. And by fast recovery, it's how fast the system can recover when the world is turbulent or is chaotic, and how can it recover fast from when it was like maybe uh, uh, relaxed, chilled, and then suddenly the world changes into a chaotic world. How fast can it recover? And then stability, how stable the system's behavior is. Can uh, can um, can it fix or can it handle blow-ups? So by blow-ups, I mean if, for example, a system lives in a world that is chaotic, uh, technically this system will have more blow-ups because if it doesn't really um, know how to handle such a world, it will have more blow-ups. So how does it handle it? How does it behave when the world is in this state? So that stability, how stable is the system? Now, and the system also doesn't really observe the entire world. It has it only observes what it cares about. So the agent only sees a partial observation of the true state. So the states of there are so many states of depending on which environment you're running the system in, it can be uh, it has many states, right? So what the system does, what the agent we want to study is how does it operate on a partial, it does operate on a partial observations of the true state. So the true state can be a large state, a very huge state, and but the system only sees what is partial, just a section of the world. Then the underlying dimensions, sorry, the underlying dynamics are changing, and we'll talk about the A and C. A and C is just the dynamics of the world. So I'll show that in a bit. And then the drifts. So there could be slowly drifts and chaotic regimes. And regime changes can be abrupt, hard switches. So as I said, the weather, for example, it's a hard switch. It switches abruptly. So the system has to follow or be at alert in that regime. Then this forces the agent to constantly test its model. So if yes, non-stationary forces agents to be alert. This is just what it means, like to test everything before it acts. And then a few stages for this project will be we'll do an instrumental we'll instrument the environment, like set up the talk about how the environment looks like, and then we will talk about what type of environments we can test in, and we can experiment in, and then the baseline plane predictor. We can also talk about the baseline, just a simple model, and then how it performs. We can also talk about that, and then understand its difficulty of tracking the regimes. And we will also talk about diagnostics in a detector. So by diagnostic, I mean like the system has to diagnose the um, itself, diagnose to see how it performs, and then make relevant changes or adaptations. And then existing diagnostic, residuals, coherence, page Hinkley. So we'll talk about all this in a moment. But this is one of the things we will talk about throughout these the streams, and then we promote them into a real change point detector. So some of the best. Okay, so current model uses page Hinkley detector. So this model is uh, it helps the model detect the changes in or the state changes in the state of the environment, and also the changes in the state of its own um, parameters or whatever it operates on, rules, etc. And then regime aware predictions, we'll talk about all this. Multi-mode process, and the detect regime changes, reduce catastrophic failures. Sometimes if in a chaotic world, systems usually fail a lot. And one of the way we want to study is how can we make a system that can adapt its model to prevent these catastrophic failures in a harsh environment. And then change aware adaptation rules. Also talk about how rules affect learning, and then how rules affect stability and memory of the system. And then we'll introduce the later on we'll after we've done the analysis of the baseline system, maybe a toy example, and we will introduce a meta ecosystem where there's some sort of meta learning in the system, or the system using some of the meta. By meta, I mean just things to help the system learn better or adapt when the environment changes. And we have in the system currently it can run on autopilot. I mean, the experiment we'll be doing automatically steers experiments and then parameter sweeps. So, but parameter changes while the system is also training or operating in the environment. And then chaotic diagnostics is just to see how the system is. Is it unstable or is it stable? How the environment is as well. And then mimetics is cultural. So this is culturally, so our system has introduced this concept of memes uh, just for experiments. So the idea is, can we evolve, or can multiple agents running in the same environment or different environment exchange uh, ideas, or by ideas, because our system is more of a rule based. Can they exchange rules, best rules, or genome in this case? So we will do, but to find the best rules, we do some sort of evolutions of a system, then pick the best genome for that system and use it to train. And then equilibrium controllers. So the equilibrium controllers are just how the plugins that keep the system in its equilibrium mode. So if the environment changes or the system uh, blows up or goes into a state of collapse or something like that, we have controllers to also we talk about how the controllers keep the system in its equilibrium. And then MetaTuner just tunes the parameters as the system learns or evolves. And we can test all this stuff in the complexity, and stage stage six will all be outer evolutionary loop. So we will evolve some rules and see which rules are better generalized in a stationary, non-stationary world. And then what we want to really answer in this research is how well can a plane, first stage is how well can a plane online predictor track regime changes without meta learning. So we strip off meta learning or learning in general, then just run the system on uh, different a different environment that has no sort of some sort of uh, learning in it. And then can we design a change point detector that reliably picks a true regime with low delay? So this is just picking the best that does what we want it to, or what is best for the system. Then can simple changes change aware meta rules adaptation windows array burst. Array is just learning rate burst stability getting significantly improved robustness without blowing up. So this is just stability. How stable is the system? How healthy is the system? And then how does a full stack mimetic equilibrium meta-tuner chaos affect regime robustness? What helps and what hurts? And we'll talk about these. Can we use outer loop evolution to automatically tune adaptation parameters to add um, robustness, and instead of hand tweaking them? So we don't want to do manual hand tweaking of the parameters. We want the system to um, modify itself and also change to get to that equilibrium. And the stream will evolve with time. We'll do this, we'll do experiments, we'll do live coding. We will also um, talk about other things as well. So for this week, I want to just introduce the project, talk about what we have, and also what inspired it, and explain why time station and partially observed worlds are good test bed for predictive brains, and introduce the metrics of regime robustness. So we will talk about all this in the coming weeks. Now, why this project exists? So we're exploring this idea of so there's a let's find it. Uh, okay, so a arc price. I think those for those of you not familiar with this the arc price, I think you can find it on the arc price page. But ideally, it inspired this project, even though they are not really um, in same direction, because the arc price, the AGI, it's an abstract. It's it's find an abstract and reasoning corpus for AGI. So it's more of pattern recognition and generalization, which of course I think it's we want to head towards that direction. So if we can get a system that can operate well in an unstationary environment, then we can have a go at maybe talking about arc price or maybe something else, So, but ideally, what the arc price is just trying to figure out how well can systems do how well can AI systems do better than do tasks that are known very well to be done by humans. And yeah, so that's mostly what inspired this project. But also there are other things as well, like cellular automata. So we know, or maybe some of you might know that uh, cellular automatas operate based on simple rules, and those rules can be changed, can be tweaked, both by manual or by just the system itself through adaptations and evolutions. So um, and they are the best ways to study such systems that operate based on rules. And then because of their emergent computation, so emergent computation means it means just that the system can run, if you run the cellular automatons, there are some sort of behavior that emerge throughout the system as it evolves or as it runs through time. So those emergence, we can see them in systems like The Game of Life by Conwell. And you can also see this system when you do experiments in just running a cellular automata um, to different tasks that involves the rules that of the system of the cellular automata. So we will take that inspiration to the cellular automata, and the goal is to have our predictive model, adaptive predictive model, run in an environment that is cellular automata environment. So if you can get to that goal and see if we can get the system to run in this environment, then we can study um, um, a lot. We can study this system through those environments. And so I've also already mentioned all this. So I think I'll just head straight to um, yeah. So this link is where the price lives. If you want to check it out. So next thing I would do is just go through the project, discuss the results, some of the results I have. So for now, we'll um, talk about. So first, let me just do. Let me see. We can't take ways. So walk through. So I'll just go through the entire project. Talk about how it's structured, where the plugs are, the configurations. And so for now, let me see. So we have default diff config. So configuration is so when we talk about rule-based systems, we are thinking of we need a way to uh, communicate those rules to the system. So, like, how do you tell the system these are the rules that you should operate in? Now, for us, we have this these configurations that does that, and these configurations has just values. You can do the seed. So, so for chaos or a system that runs in a chaotic environment, or, or any system. So if you want, um, you can introduce some randomness to a system if you want to really understand how a system does. And randomness is a good way to study predictive system. So although it's hard to predict a system in a random in a random environment, but randomness is a good way to do that, to study such systems. So I just talk about a few plugs. The seed is just controlling the random, the pseudo random behavior, and then now this is not important, but autopilot is just it's a flag or plug to turn autopilot on if you want the system to run on autopilot. And then we have a few genomes. So these are hyperparameters that can be tweaked by the system itself. So we can feed in default values, run the system, or you can evolve the system and use that genome to study the system. It controls just how much um, how which is the best genome you can use the system in. So pi up, pi down just controls the basing. So if you, I'll talk about pi as in precision. So if you go to I have a section called precision. Let me find it. It has to be so precision is just it controls just precision or attention gain of the system. So if an environment changes, we, prediction will tell you how the system attends to changes, like how it pays, how attention gain has affected the system. You see some spikes or not non-spikes when there's some sort of change in the environment. And then we have where it starts main pi learning rate. So you change the learning rate, it's C. And homeostat is just the so it measures the health of the system. So if a system is it's healthy, you if you want to know if a system is healthy, you'll see these plugs. You will just measure these configs. And also we have some health configs. And memetics is I talk about culture, so introducing culture in the system, running different agents at the same time, and a few plugs as well. So we can't talk about all these plugs, but they're just the rules of the system. Tell it to do this. I mean, you give the system the rules, and then it will use those rules to learn, to adapt, to do all sort of things in the system. And then we have also plugs and plugins for the system, and then different environment. So for now, for the default, I think okay, so there's also mod if you want to change it to run a single mod, multi agents. But let's see, I want to find the environment. So the environment, so I have different environments. So I think I'll just go to this and see environments. So I have a toy environment, which is just what we will start to do some experiments with. So it's a toy environment where it has a few states, changing the state of the environment, loading the state of the environment when you have, for example, evolve a genome and you want to uh, put that into consideration of the environment later in time, you can do that. So I think I have two types of environment. So the toy environment and then richer environment. So richer environment, I think I'm using richer this environment where you can run your agent in an environment, mostly 2D environment, and then you can run um, you can train your agents in such an environment, and then I think so. So those are the rules, and then we have the project set up in a way that we have autopilot. So if you want the system to run on pilot, diagnostic device and the kernel of the system. They evolve. Evolve. If you want the evolved genome, you can also um, evolve a genome. So let's talk about uh, results. So I think so. This is just the code base. This is where we will be doing most of the live coding and also debugging or like trying to understand what the system does. But maybe I should talk about one of the plugins. I think, let me see, I think this self-tuning nervous system. So I think this is the plugin that I'll show you once I have the result. I show you the results. So there is some of the results I have. So the reason why we are doing this live is because I ran into an interesting thing. So when I was doing experiments for this. Let me just find um, a few results. So so the config, let me open this config. So I have this configuration. So this configuration is it uses a single agent, just one agent, and um, the genome is basically the same. And so what only changes is a single. What changes is we turning autopilot off and a single mode, and also we are turning um, the environment to so richer and a toy environment. So toy environment is just a basic version of it. So it's not too noisy. It's not too chaotic. And so I ran this. I trained. So I think which was it? Let me find the experiment for this. Phase one. Was it phase one? Oh, this is config. Okay, let me see. This is three. Thinking it must be here. 1A, 1B. Phase 1A. So the logs. So this is the logs. Okay. Uh, all right. So let me see. So it's in agent multi-agent 16. Okay. So I will just go to multi-agent 16 phase 1A logs. Mm. Oh, again, just to mention a bit something. So I'm running training using. So you supply the config, run the training. So you can so training. I think let me just go here so it's clear. So I have yeah here. So you supply the config for the training. The configuration takes the default one if you don't supply anything, and then you train it for some time. So um, for the for this version that I want to show the results for is I think I trained it using this. Yeah, so for 50 steps. So this is a lot, but we can run training now for 20 steps and just see I'll leave it to train, and I'll just change this to I need this config and change this to this. Yeah, I'll change this to from 15 to I think it's 15, not 16. So 15 is phase one. Oh, okay. Did I put 16? I'm at 15. 15, 16. Okay. And so I'll change this to which was the last one. The last one was 20, 27, 28. These logs will be version 28 and 20, 20K steps. Now we'll run this training for now. And so I'm running on GPU. So you can set device right here, and then it detects which device you're running it on. So the training will run, but what I'll do now is I'll just show you the previous results I had, then I'll show you these other results later. So this is phase D. So without this is without autopilot on, and then without the other plugins. So if you go down in the config file, we have plugins. This is also set to off. This is a self-tuning neural system is also off. We just want the base model, the simplest of the models, and see how it performs in a toy environment. And the environment is also in a toy environment. So I think where is it? Yeah, here. It's a toy environment, not noisy, a bit of noise, noise sigma, and then switch also is off. So by switch, I mean, so we have two basic dynamics. So we have dynamics A, dynamics C. So dynamics C just controls what the system focuses on, like how it changes. And then dynamics A is just the hidden the latent dynamics of the system. So in this case, the actual dynamics or the of the environment. So it if it keeps switching, if switching is on, then the environment will be shifting all the time. Now the system has to track that. But if it's off, I've set it to off. So this is the simplest environment possible. Nothing is switching, it's just static. The environment is static in this case. And then we also turning meta tuner is also off. Basically, what we it's like we have no good stuff in these rules. There's nothing special about this run. It's just simple, basic bare run of the system, and also a few mimetic is also off because it's one single system. And other things are also off. We only have the diagnostic of the system to just tell us the diagnostic of the system. This is for richer, then regime. So regime is also off, so the environment is not chaotic. So there's no change in the regime of the environment. It's just simple run. Now this will run for at least the next few. But I will oh, so I do the experiment on Mathematica. So for those of you who are not familiar with Mathematica, it's a a notebook environment for doing some sort of computation in whatever field you are in, maybe mathematics or physics or whatever. But yeah, so it's a good way to visualize stuff also. So we'll run this, and this will open the data, this CSV, which I think I should also open it somewhere here. So this CSV has a few fields. I'll only pick the most relevant fields for now, but all these fields are here, and we can talk about what we care about right now, which are these columns. We have coherence. Coherence is just tracking how the system is performing and between each step of the run. And coherence hat is so this is more like realized. There's realized coherence and then focused coherence. So realized is the current coherence. So by the current is if you're in current state and you have a predictive or predicted next state, like say y predict, then the current minus the predict is what realized coherence is. And then we have predicted or focused coherence, say the next coherence, how well would the system perform in the next step or in the future. You can give it as much as a window, as much step as you want, but um, in this case, I think for the toy version, for this simple version, we're doing just one prediction step ahead. Then we another one version, another one is pi. Pi, if you focus on pi, you will. Oh, let me run this first and see what it shows. So if you focus on pi, you will see. So this is pi. It starts off. So this is a previous run. So coherence is. Uh, let's see. It's hard to see how it's behaving right here, but coherence keeps it's up there. It's a bit up there. So 9.0.99. So that's good. It's realized coherence is better. It's doing well. And to really see how the actual system really behaves, you look at pi. So pi tells you um the precision, like how the precision of the system or attention gain. So if so it starts off let me see, let me expand this. So we can see from, and you can compare pi plus I think chaos, where is chaos? So chaos is right here. And you if you compare these two, um you will see that first of all, like the pi starts off and then spikes. It tells us something happened in the system. That's what us programming this in the system. Like, but it's something happened around this step, right? It's for step for 60, something happened. And if we go like we just track these and then the system goes on, um, it goes well, it's smooth at the beginning. It's the system isn't it's comfortable, it's not paying so much attention. And then uh, at around maybe this step 3,000 to a couple of 12,000, it's it's a bit it's playing around 1.19, and then spikes again. Then here is where things gets weird. Now here I think what I think the system does, because you can see also here where A effective is just the environment effective now. So um, how the system or how the environment dynamics have changed throughout the time. And we can say here it's too spiky. It's spiking a lot right at this point. And we can interpret also this data in the sense that, I mean, like it's more relaxed, I think, at this point. Then when it gets to um, towards the end, then pi starts to spike a lot. Then this spiking just means the system is uh, it's paying so much. The attention is it's a lot. It's going up towards um, towards 3 point. So we set pi for this case. I think we set pi max to where is it? Pi max to 3 point. Yeah, we set this to 3.5. Pi main is 3 point 6. Now, so the system is just hovering around 1 and maybe uh, 2.8. So towards the end, the system spikes like I mean pi spikes a lot, which means that the system is paying a lot. The attention gain is a lot once the system has trained, and then it's confident enough in towards the end of the run, then starts to pay attention. And we if you look at chaos, it's more balanced. There's no overshoot of chaos. Like this toy environment has it's less chaotic. There's not crazy things happening in this toy environment. And um, uh, then we have predictor learning rate. So I think learning rate for the predictor is it's going down for this case, but not that it's not that bad. I think um, it gets worse when uh, it's not predicting very, it's not learning to predict very well. Now that's when it gets really, really bad. And then we have energy. And also, one other thing I should mention is that the system also has an energy mechanism to use energy in the sense that it balances energy. It uses more energy when the system is it's very bad, chaotic. I'll show you the results for the run. But so this is we will compare these results and where the results the results uh for this let's see. Okay, autopilot. So if you run it on autopilot, let me just compare these results with so this is just plain. Let's say we switch this environment to chaos plus no chaos toy chaos, right? Uh, so we have some sort of chaos, same autopilot is off, and then chaos is we have yeah, we have introduced sinusoidal random walks. Random walks is a system just doing random walks in the environment. So we want to see these results. Plus chaos is also turned on. So we want to see these results. Compare that with let me just open you or just copy this lab 15. Which one is this? 52, 53, 52, and open. And there you are. Okay, now I will change this to which one is this? Um, phase three. Phase three was 20, so 20 is 20. So phase 3 logs, I will use phase 3 logs. 3A. Then agents, just agent. So 20 here. Yep. And run this and compare this. So we will compare with a bit of chaos introduced, and I'll just, yeah, so chaos is on. I think this there's some sort of uh, yeah, so I will compare this with this. So it looks like it's spiking a lot in this version. The chaos are spiking a lot. Oh, and we can also see I think numbers are better communicator. So coherent in this run, it's 0.9992. This is the mean, 9238. And then in this run, we have 0.996. Uh, so coherence it's better when we have in this version we have it's a bit higher in this version. It is 3 point which one is this? Phase 3A logs, where we turned on a few plugs. We turned on chaos and we turned on um, we switched on a few other plugs like sinusoidal state, and then random walks switches is also on. This means that the environment is also switching on and off. But we can see that the results, okay, the K it's more spiking on this version than the earlier version. And I think let's see what pi is saying here. So pi is saying 1.85 on this version, and without on the base version, and also with chaos. So, and this says that pi is what is it, 1.81. So it's a bit high on this guy, on this when we turn on chaos, pi it's a bit high on this run. And what is the median? 1.7, 1.9 here. So, and then we can see here that we can compare how pi is also performing coherent. So coherent is what is that? Better if effective. So better effective is just plasticity. So plasticity um, um, of the system. So we can see that it's relatively not really spiking a lot on this case. Only a few steps where 1,000 steps where it went a bit higher. And we can see also the results here is says 0.02, and the original version, where is it? Okay, the original one was, I think I have this here. And yeah, so also energy is, which one is using more energy? So this is 0.00059. This is 0.000060. It's not so it's not a lot of difference. So they're both they're both using a bit of energy, but so the whole let's compare pi for this case and the other one using these plots. And so it's wavy for the so for if you turn chaos on, you see that pi is it's wavy, it's wobbling a lot at the beginning, and uh, the toy version, it's the whole toy environment, but without chaos and other plugs for the environment. We're not switching the environment a lot. So this version is not switching the environment a lot, and we can see that from the configs. So configs for these where is it? This. So for this version, we have switches that set to on. So every step 50 times steps 50, we switch the environment. We shift the environment. It's like shifting the environment where the agent is in. And this one is the other one is where is it? The other version was it 16 or 15? Yeah. So this has now, let me open them side by side so see what's up. We compare. So we have environments. Where is environments? Uh, yeah, there. So we have toy, same toy, and noise is the same. We basically these are the same. The only difference is we introduce Nisodol uh, on this and random walks on A. So A is the dynamics of the environment. And also we switch A a lot. I mean, every 50 steps we switch A, we drift A. We don't drift A on this config. So, and that's why we see on the ones we don't switch A, it starts off smooth, everything's like smooth, and then spikes. The only spike starts at 12,000. I think where is it? 13,000 at around 13K steps. Then it spikes. For this other one, the spike starts. It's wavy a lot. Uh, it says that the system is realizing that there's environment is switching a lot, so it has to pay more attention. So you see a lot of spikes on these run. So once you do, you get to the spike like was 9,000 9K, around 9K we see a spike, but this started from 13K, and then it's just does kind of just does the um same towards the end. It does the same, uh, maybe not the exact same because of there's some sort of differences, but it really just goes towards upwards attention when you run the system on more steps. And the more steps you get, then you get to see this wavy towards the end. And we can also compare plasticity. Plasticity is the same. Let me see, is it the same? Plasticity of the system. And see. And I should apologize that I haven't gone through all um these fields. It might be confusing right now. I think we should if we have time, we should go through all these fields so that it's clear to understand which field what each field does. I think I'll make a document for this so that I include on the stream so people can follow these fields. It's cryptic right now, I think, and probably doing a bad job explaining what they are. But let's see, where is plasticity? So it's for the first run, we have this plasticity. It looks different because yeah, it looks quite different for this case. So the second run was this when we turned some plugs on for environment, and we see plasticity behaving. It's doing a lot of waves that it's smoother on this step. So plasticity is just controlling what how pi. So plasticity and pi are go hand in hand. So you study once you do like pi might affect plasticity, and I mean attention might affect plasticity, or plasticity affects attention. I think plasticity affects attention more than pi affects plasticity. But uh, yeah, I think the more plastic plasticity is when plasticity is high, I think pi attention seems to go up, I guess. Well, yeah, I think I need to look into that. But interpreting um, uh, pi and plasticity in hand should give us some insight on what the system is doing. The where is it? Where's pi? D. Okay, I think I lost pi. Oh, yeah. So pi and plasticity. Okay, something is blocking. There's a lot of these one. Yeah, so okay, for this case, I think I'll just do a few talk through the I don't know how to make this slide so we can see all of it. But these values are will like if we can go through all of the I've just given you an overview of the results that have been like finding along the way. I've not talked through all of them. There are lots. For example, I have this where this version, what version? Phase 1B, where I turn off some things. I think some values, or which one we changed here? I don't remember, but some values changed. It's not really different from phase 1. And so phase 2 is just switching. a turning switch for the dynamics of the environment back on and off. So switch is on for this A, and then switch is um, on for for C, not for A. Yeah, there must be something I changed here. And then we have chaos and chaos. So we have chaos and chaos autopilot. Autopilot is just control pi if pi not pi but pi up. So we have pi up and pi down. So pi up and pi down is basically where we want pi to play. If it overshoots at pi up, then autopilot will make sure that the system adapts. Pi also adapts with pi up and pi down. But let me see, did we? What I want to show is a different environment where we will see some strange things happening, and this is when we run the system with this config. So this config is just I'll just do uh, which one was the last one? Uh, I think was it 20, 28? So we need 29, and we will run. So this is the state, the observation, and I think what we want is richer. So we want to run this agent in a richer environment, and richer is just this part of the environment. And let's see the code. So the code is really so yeah. So we we just set up the environment in sorry, blended. So the richer we just tell it which environment we want it to be in, and the latest version is version 5, and we run that environment in we run that agent in this environment. This is a more it's how do I say this? It's like it's a lot of it's a non-stationary environment to be specific. It's not like a stationary environment in the toy environment. Now what we want to see in this environment is what the system is doing and how it behaves compared to the toy environment. Now I have results for this, but I want to just run. Okay, so this was done. This is done, and I will just use try to I'm expecting it to be the same or like a few differences, but let's see what this did. And where is it? Uh, 28, 28. Reload these 28 logs. Okay. We yeah, I think we just find well, okay, this is for just 20 steps, so I think there's not a lot of differences. Let's look at the mean. The mean should tell us. Oh, shit, I don't remember what the mean was for the last one. Coherence. Let me find it here. Mm, okay. Yeah, I think it's not much difference. But let me just run with this richer environment so we see. maybe it's a bug, maybe it's not a bug, but we will see. Let me run richer and 20 steps, and then I want it to go on this 29 folder. And what else do you want? I think that's it. So let's run this, train it for like 20 steps and see what this config does. But okay, so some of the earlier results for each, I think, do I have earlier results? Okay, let me see. I must have something here. Okay, can't see. 27 was the last. Let's try B. 54. Okay. Let me close something here. 53, 54, and 27. Okay. These. Now we'll pay attention to how so in a richer environment, coherence like this agent performs pretty bad, but I don't understand whether it's a bug or it's just an emergent property for this agent, but coherence is it's below it's really down. It's 0.228. The others were operating on 0.99. So and when we look at um, where coherence starts to really go down, like misbehave, it's around this step 22540. And at the same time, we can compare pi, how it looks, the attention. So in a regime environment, the agent, uh, like the agent is above pi max. So pi max was 3.5, I think, and the agent is operating around pi max, which means it's paying, it's trying as much as possible to keep up with the chaotic environment, with a complex environment, so to speak. So it's a its attention is and precision is it's so high, um, almost to the max. So it's operating right there, and we can see that through the lens of chaos. So if you look at chaos, this is a chaotic environment. It's the maximum is what 0.79, zero point 0.8. That's it's always up there throughout the run. So it gets really well, and you can see it from the very beginning, from step zero, from step zero to around 2540, which is the same step that coherence started to misbehave. So from this step, it's doing well, and then once chaos overshoots, chaos just once the system becomes so chaotic, then by so chaotic you can look at the numbers here. It's stuck up there, 0 point it's so if you clip the I'm clipping chaos using 0.95, so minimum is 0 and then maximum is 0.95, so it's stuck up there around zero point 0.8. Now what this tells us is it's a lot. Like I can't decide whether it's a bug, but what we want to do throughout the system is figure out why, especially if you look at precision pi, what does it tell us about cha non-stationary environment, chaotic environment, and then what the system does. And it seems like pi doesn't really blow up. It's still it's still trying to keep up with the environment, and um, chaos is just stuck there. So once chaos is stuck there, the system can't really. There's no way to get out of that state. It has maybe it has interpreted the system as this is it. Like we are in this state forever. Like we can't change from this state. So I have to be paying more attention to my environment. I have to be very alert all the time. And so that's why you see coherent dripping downwards. And stability. So even though even though the system is um, it's behaving like this in a chaotic environment, we can see the stability. Okay, from this you can see that it's stable for some steps, and then it starts to get unstable, spiking a lot, and that tells us something about what's happening with the system in that environment. So what we want, the goal of this is to understand why this behavior is coming up, whether it's emergent or it's a bug. So the whole of this series of streams will be just to understand what's going on on this system. So to we compared the toy version. It's doing this is in a toy environment, by and in a toy environment it's just doing okay. There's nothing, no noise, no strange things happening. But once we introduce richer, then we get this sort of behavior. Now the goal is to understand what this is, um, and to hopefully get if it's a bug, we fix it. And if it's because if you run, I try to run training for more than 20 steps, it's still stuck up there. And you can see other plugs, the way they behave. You see, around that step, we are just, doing um, like the system's trying to keep up with the environment at all cost. And we can see this with energy. So energy drips really down. So around that, energy goes down. It's using up a lot of energy when in a chaotic environment. And we also you can see the energy budget at this point. It's going really down, compared to these. Energy is s- it's not like it's balanced in terms of how it's using energy. And budget, it's also not so, like the budget is constant. It hasn't used up energy until budget is finished. But for this case, for this rich environment, we see a lot of energy use over budget, until the budget finished. Now, the goal of the autopilot and meta tuner and equilibrium, which I showed, is to make sure the system is not it still works in a resume environment, turbulent environment, and making sure energy is using up energy well, doesn't use up the entire energy, just in between. And from these, we can see that energy is being used up a lot. The system still works. We can see that from precision. It's still um, trying its best to keep up with the chaotic environment. It hasn't it hasn't had a meltdown, like break. Um, it's the system is broken completely. It's not doing anything. We can see it's doing something. It's paying attention, but what we don't know um, is how to keep coherent. Um, well, like coherence just measures how well the system is doing its learning. Now, how for this case, it's not learning anything. Coherence is down 0.2. It's down, and we want to understand this. What is this? What is going on? Now, I think yeah, I think we're mostly out of time, but so the goal is for this stream today, we wanted to go through the objective, which is learn about the project, why it exists, and what inspired it, and explain why non-stationary partial observed worlds are a good test bed for predictive brains. And what you can see that right here, like prediction is it's performing really bad in terms of predictions. Coherence tells us like it's really not predicting things really well, and we will learn these throughout the stream and then introduce the metrics of regime robustness. So we introduced Rita, and we have seen a lot of crazy things going on, and then outline the stage map. So this, I think, evolutionary, we will run through the system. Throughout the system, we'll run through the evolution of multiple agents and then see how different agents perform. And I think we have covered most of this. Oh, diagnostic. So diagnostic is, let me see. In the plugins, we have diagnostics. Is it? No, it's I think it's here. So diagnostics is what keeps alerting the system if something is wrong. So chaos, right now we don't introduce any chaos in the system. We use diagnostic to for the system uses its own diagnostic to measure how much uh, the environment is, how chaotic is the environment. So the chaos is something that we we don't introduce into the system. We just diagnose the system. We diagnose the environment or the system and tell so that it knows how how chaotic is the environment and how to go about its learning process. And I guess yeah, I think I don't know if we have any charts, but yeah. So that's all for today. I want to let's see if I have any charts. I don't know if I have any charts. Uh, uh, yeah. So Dugan says okay. So there's no questions or anything, but yeah. So that's the goal of the project. We will go through all these steps. And I will I think the next step is really to just do more experiments with first of all to discover whether this is a bug or just emerged. I'll run behind the scene a few more steps, like 2000k steps, and see whether towards the end it really comes calms down or it just keeps going. And um, yeah, so that's it for today. Thanks for joining me, and I'll see you in the next stream. Um, case.